Now we are going to continue our discussion on the exponential form of complex numbers. Recall that a complex number can be written in polar form in the following way, where r and theta are polar coordinates of this complex number. Now we are going to use Euler formula to simplify this expression, and this new expression will be known as exponential form, and it will help us in simplifying many operations on complex numbers. Now what is Euler formula? Euler formula is given by this expression: e raised to power iota theta is equal to cosine theta plus iota sine theta. Now if we are given a complex number in the following form, then this expression by Euler formula is basically e raised to power iota theta. So the exponential form of complex number becomes z is equal to r e raised to power iota theta. Now we will learn about these exponential functions in our later discussions. Now let's consider an example. Now we are given this complex number, and this complex number lies in this third quadrant with coordinates -1, -1. Now we have seen in our previous discussion that the polar representation of this complex number is given by, so the r coordinate is square root 2, and theta is basically -3 pi by 4 plus iota sine -3 pi by 4. Now we are calculating this angle in a clockwise direction, so that's why we are taking it to be negative. Now using Euler formula, which says that e raised to power iota theta is equal to cosine theta plus iota sine theta, we can write down the exponential form. So the exponential form of z is given as, so z is equal to square root 2 exponential and then iota -3 pi by 4. Or we can also write it down in the following way: square root 2 e raised to power iota -3 pi by 4, or we can also write it down in the following way: minus iota 3 pi by. So this is the exponential form of this complex number. Now we also know that argument of z has infinitely many possible values. So we can also say that this exponential form has infinitely many values. So a given complex number has infinitely many exponential form. So if we are given this complex number in this exponential form, now this complex number can also be written in the following way: r exponential iota minus iota plus iota and then -3 pi by 4 plus 2 and pi. N is any integer. Now these are all the infinite many possibilities of the exponential form of a complex number. Now let's consider some special complex numbers. So the numbers where this r coordinate is always 1. So in other words, the exponential form of this complex number is given as e raised to power iota theta, since r is 1. Now if we consider Euler formula, if we use Euler formula, then these complex number become this, and the modulus of these complex number is cosine square theta plus sine square theta, which is equal to 1. So we can say that this implies these z are located on a circle of radius 1. The complex plane, this is the situation. This is unit circle with center 0, 0 and radius 1. Okay, so in particular, so what are the complex numbers? So what are some particular values of complex number lying on this circle? So this is complex number e raised to power iota. So in this case, the values of theta would be 0, or we can also take it to be 2 pi. Now similarly, let's consider this value. Now this is equal to e raised to power iota pi by 2. Similarly, if we consider this complex number, then it will be equal to e raised to power iota, and the value of theta is basically pi, iota pi. And similarly, we can also find other values on this circle. If we consider theta to be equal to pi, then we have seen that this z is equal to -1, or we can say that e raised to power iota pi plus 1 is equal to 0. Now this is known as Euler's identity. Euler's identity is one of the most fascinating identity of mathematics, since it involves many important mathematical symbols. So starting from pi, so the symbol pi has been used in the works of Hippocrates in 400 BC. The next symbol we can see that is iota. Now this iota is the main focus of this course of complex analysis. The next symbol that we see in this identity is this e, which is the base of natural logarithm. So hence an important symbol. Now these two symbols are two basic operations of mathematics, and these two whole numbers are two basic foundational whole numbers in mathematics. So this, every quantity, every symbol of this identity is important. Now let's go further and consider the case where the value of r is any positive real number. Now in this case, we will get complex numbers which lie on a circle of radius r, capital R, and the center of this circle is the origin, 0, 0. So more generally, consider this equation. So this equation says that we are considering all those complex numbers z whose distance from this fixed complex number z0, so this is a fixed complex number, is constant. So this r is also fixed constant. So we know that the modulus of z minus z0 is basically the distance between these two complex numbers in the complex plane. So this equation means that set of all those z complex numbers whose distance from z0 is equal to this fixed constant r, and by definition this becomes a circle with center z0 and radius r. So there is another way of writing down the points of this circle. So this is equal to z0 plus r into iota theta. Now we know that the complex numbers of the form r e raised to power iota theta are points on circle with center 0, 0 and radius r. So in other words, these are these points. Okay? So these complex numbers are basically r e raised to power iota theta. Now if we add z0 into all these complex numbers, so in the vector form we can say that if we have this complex number on this circle, let's say z 1. Let's call it Z1. This is the vector. Now we are adding the Z0 vector. So this is the Z0 vector into this vector, and hence we are getting, this is the Z0 vector in the parallel, and hence we are getting this new point which is Z1 plus Z0. So in other words, in the vector form, we are getting points on this circle, and then we are adding Z0, and then we are getting the points on this circle. Or we can also say that we have translated this whole circles in the Z0 direction. Now let's use our knowledge of exponential form to solve this equation. Now we know that if we are given Z minus 1 equal to 2, then this is a circle with radius equal to 2 and center. So this point is basically the center. So in this case, this is 1, 0. And we also know that if we consider Z is equal to e raised to power iota theta, then this implies it's a circle with center 0, 0 and radius 1. So if we want to solve this equation, then geometrically speaking, we need to find the intersection of these two circles. So let's consider this complex plane. So let's first sketch this circle and let's call it S1. So the center of this circle is 1, 0 and the radius is 2. So in other words, this is 1 unit, this is 2 unit. So we will be getting circle the following form. Okay, and now let's consider this is our S1. Now let's consider this S2 circle. Now this S2 circle has center 0, 0. This is the center and the radius is 1. In other words, it will pass from this point to this point. In other words, we will be getting this circle. So this is S2. Now we can see that the point of intersection of these two circles is basically this point. So we can say that this equation e raised to power iota theta minus 1 modulus equal to 2 has solution theta is equal to pi. So only for this value of theta we will be getting e raised to power iota theta minus 1 modulus equal to 2. Now we have seen how to calculate exponential form of a complex number and how we can do simple calculations using this exponential